Okay. We are going back to the class, so it's 59, maybe, okay, let's wait this minute. In the meanwhile, maybe if there are questions and about the exercise and someone that wants to report their findings, it's welcome. So, any of you that has questions? Yeah, then let's move on. And let's go to another example that you have seen yesterday with Yannis. That is the case where we do a rotation around, you apply the rotation, a unit transformation of a set of coordinates, and we rotate them and shift them and get out the two arrays with the results. So this is an example that yesterday you saw with Yannis and got a number for it. So we would like to see how is the same performance in this case. So how do we implement it in Python? Well, let's implement it in a simple way. What do we need? We need the two set of coordinates, x and y. We need a list of angles, and we need the shifts. Then what you want to do is to compute the cosine and sine of the angles and obtain the two new set of coordinates by rotating and shifting. So this is namely what is written above. Again, this is the Python implementation that we run in both cases. What I'm going to change now in the results is, for instance, the fact that the data size now has changed. Before it was set by default to be 3 arrays, but now we are going to have 5. We have 5 arrays as input, sorry, 7. We have 5 arrays as input plus 2 as output. So we need to be careful that when we check the bandwidth, we need the data size, our IO is 7 arrays. Times 8, it's because it's double. And basically, we can see again a comparison between Numpy and Cupy, where, okay, Cupy is significantly faster than Numpy. It's about 160 times faster. And we have, if we look at the bandwidth, though we are not saturating it really, we have about 200 gigabytes per second bandwidth. So this should be compatible with what you were getting yesterday with Yannis as well, with not optimized implementation. So one way to optimize it there was to correctly use the correct number of threads and blocks. Here we are not going to check that. We are going to compile it and to compile this kernel. Again, this is, I had in mind to have it as an exercise, but maybe for the sake of time, let's move forward and then let's do it together maybe, or yeah, let's do it together like this. Let's take the exercise and do it together. So this exercise 3, we want to write a kernel for it, and I will copy these 2 functions and paste it in. So this is the function we want to implement, and this is the kernel. Let's translate it. So we need 5 inputs, right? So these are here, 2 outputs. And then we want to write the operation. So at the moment I'm just assigning, we want here to write this math. Can somebody help me? What do we need to do? So you can also try to do it within the exercise by your own. So we want to do exactly the same, right? So let's copy and paste what we have here. Okay, is this going to run? Well, it compiles, but does it run? I mean, it's not really compiling, it's not complaining, Cupy, but will it run? So if you did some experiments, you should have seen how this how Cupy gives you errors. And let's start with something on size 10. Let's call the function. What error is it going to give me? So if I try to run it, okay, doesn't run. Why? You start reading and you get the the compiler error, expected a semicolon. Okay, there are two errors actually. Identifier XP is undefined and expected a semicolon. Indeed, what we said we have to do. We need, this is C, so we need to put semicolons, and we need to use math operation. Here we are going to have a clash in the naming, so you need to be careful because this cost now is a function, so I cannot assign the value to a function. Let's name it CS, SN, and let's use CSSN, that is something undefined. Okay. So this, it's a better kernel. Is it going to work?
I have to use, but maybe the math function.
Yeah, these are the math functions. These are available. Cosines in it's already loaded. Okay, so you don't need to say something. But still, is it going to work? Let's try it. Still errors. What is the error? Identifier SN is undefined. These are C-style errors, so you need to be a bit smart about that. What is the problem now? That we didn't define the type of them. So it's C. You need to put the type of them, T, and allocate. Okay, this is the final kernel. Is it going to run? It does. All right. So you need to be careful. I don't know. Did you play a bit with the element-wise kernel? Did you run in this kind of issues? I know that by submitting job is more boring. You need to check the output and see the result. And interactive is better. Okay, so this was the kernel, the compiled kernel, and now still C, and now let's run it. Overload the function. What did you do? You run this? I mean, this runs in my case. Okay, maybe you defined. Sorry. You named it in the same way with another function, or what? No, I didn't change I see you used cos. Okay, I see. Yeah. Okay, so we run it, time it, and well, easily enough, we're getting a much better performance and almost the expected bandwidth. Okay, it's around 685. Still not great. Yesterday, Jan showed a few other tricks that to get the best during. I don't know if you want, we can try to implement them. But okay, this is already good enough. We have, if you compare with the Numpy, we have again, a great speed up. It's 550 times faster. Again, a factor of 4 times faster than the non-compiled version, and it's good enough. So these are cases you see now. At the beginning, we were talking when it starts to become more useful to use Cupy versus Numpy. And these are cases that you see as more calculation you do also pushes the limit on the left between the comparison between the two. So now the compiled Cupy kernel is already faster than Numpy on about 200 elements. So it's much different than the very beginning where for the difference, for instance, you needed 10,000, or we said before for the X plus Y, you also need about 100,000. So it's as more complicated things you do, also it's helping you to reduce the threshold where you start gaining or moving to Cupy. Okay. So now I will move on to Numba, but before moving on, maybe I just want to give you one more chance to ask questions in case to help you with specific kernel that you wanted to try to write with Cupy, that maybe you use in your calculations, so you were having problem to do now in your exercise if you try to do so. So, other questions in general? Okay. If it's not so, let's move on to Numba. Numba, what is Numba? This is my last slide. Very simple. Anyway, again, just a collection of information. Numba, what is it? It's a just-in-time compiler for Python. So we are going to do something very similar to what we did so far, but we do it by using Python, using everywhere Python, never moving to C. Okay, so if you have some problems with C and you found out a bit too difficult what we were doing now because you get errors like for a C compiler, etc. You didn't really, you didn't have enough experience to do that in C, but you want to do it fully in Python, then you can use Numba. Again, Numba, it's a package that comes distributed via pip, it's easily installable, and you get two environments. One is the standard environment of Numba, which defines a JIT function, that's mostly what you want to use, which is a just-in-time compiler in this case. And then it's the environment for GPU that comes under Cuda. And under Cuda, you have again another JIT function that in that case is for compiling on device. We had some tutorials in the previous workshop. We had some also tutorials for Numba. I will just go fast over it. Basically, what Numba is asking you to do now is to explicitly write the operation you want to do as an explicit loop like this, like we are doing, like if you want to do the rotation, the shift, you need to explicitly write a loop that loops over the array and does the math you want to do. So you need to write again more C-style code, but using Python. The reason for that is that what is going to do, Numba is going to translate this Python code to C code and then compile it for you. So you don't lose the performance. If you would run this in Python, it would be terrible. You would have the worst performance ever. So the best is to do it with using only Numpy like we did here. But if you're in cases like we're discussing before, like Nicolas asked, or cases where you find it difficult to use Numpy by itself because you have more in mind the C-style structure and you want to write for loops, then this is the way to do it. You write a for loop over I, you compute, you access explicitly the elements. So we compute the two cosine sine. We do this, we access explicitly the coordinate x and y. And then we write to the output we write into the output the result. Okay. This in Python will perform terrible, but you just say JIT this. I'm using it as a function, but you can use it as a decorator as well. Like this, does the same result. Just that now this is going to be compiled. So you say JIT, you ask to compile the function, it will compile it for you. And now if we run this kernel via Numba, basically we still have the Cupy timings, but basically what you get here is a kernel that, it's not an incredible speed up. It's slightly faster than Numpy. So it's 1.4 times faster than Numpy, but it's a speed up. It's what you can get as a speed up on CPU. So this is telling you that when you are using Numpy, this is already good enough. Okay, there is not really need to go, like I was anticipating at the beginning, there is not really need to go to write, to compile kernels for functions that you can already do efficiently in Numpy. This is not so much the case when you do something like rolling. We can maybe have a look at that, since this came up before. If you want to roll, let's say, it was asked before, I want to do I want to take an array X. Is there a question?
Yeah, Simone, just a quick question. Is Numba able to read Python functions like range or enumerate?
Okay, there are some mapping for those. So the built-in Python function are available, and yes, it's going to implement them. Any function that is explicitly written also is available. So if I write my own function, Numba is going to dig deeper into the code and retrieve all the information about, so if I write my range, for instance, it's not going to complain about that. And let's return range of n. And I use this one, it's not going to complain about that because it knows how to access the information about the functions. Yeah. You may run into problems when it's not a pure Python, you're not going to execute pure Python code, but it's based on libraries. So Numpy is mapped, but something else that comes like a library, let's say, I don't know, some SciPy function, anyway, something that is not explicitly written in Python, but is then it relies on compiled libraries. Then if it doesn't know what they do, it cannot. It might try to call them, but yeah.
I have used JIT. They use this no Python option.
Exactly. There's also the no Python option. Exactly, to tell you whether to make sure that everything is compiled. So yeah.
For me, at least, when I include range or enumerate or these Python built-up functions, I cannot run. I have some warnings or errors.
So if I don't even underscore.
what I do is to basically make a Numpy range instead of range.
Yeah, I understand. No, it does not support option. Okay, okay, we can look at it, but
Okay, I was just wondering if it, it may be hardware problem. I don't know.
maybe depends on the version of Numba that you're using. If you see now, I use Python, and it has run. So I think it's a matter of the version of Numba that you're using and how far it got.
Okay, thanks. Maybe I tried to update. Anyway, thanks.
Yeah, be that. Yeah.
Just a question. So if we compile with JIT, do we expect to have performance like a compiled language? More or less,
yeah, definitely.
Compare with C, for example.
Definitely. This performance should expect. Just what did I want to say? Just it's not as great as, it's better. It's not as, most of the cases, it's not as needed as for device kernel. So this factor, it's a 40% gain, what we saw here, but it's not a factor of 400% gain. So
I'm not asking with respect to GPU, a normal program.
Yeah, sure. But just that the point, what I want to say is that you still need to do the work of writing explicit loops, which is might be quite annoying if you have to do it for everything. So you don't want to do that. You want to use Numpy. So that's not my suggestion. You should do it. You should JIT when these are becoming bottlenecks. But on the
sorry, so we can't use JIT with Numpy.
No, you cannot JIT something like this. If I ask to JIT this, okay, there is no for loop, so it's not really going to JIT. So if I use Numpy, I mean it's not going to change something. You need to write explicit for loop. It's not going to pack operation together. Okay. So
especially like specialized for loops, mostly.
Yeah, you need to write explicit for loop. That's the point of it. Okay. That's, so it's good for cases like we were saying before. In case of add row, the role, suppose the add next, let's say, where we want to do this reduction. So like let's compare it. Basically, what we want to do, it's to get y equal x plus x of y plus x of y plus 1, like was asked before. Okay. So this case, let's say with an example. Basically, what you want to do is what we do here. We say we need to allocate the output unless it's given. So, okay, we need to allocate it. This is going to be empty like x. Then we take the length of x, and then we say out. Why? So just to show you, in this case, when we do this, it's going to be quite faster than pure Numpy. So the best Numpy call is to do x plus np dot roll of x comma minus 1. Okay. So this is one. This is one case, this is the other case. Let's run a comparison. So you also have an idea on how to do on the chain, if you want to try out things on how to use these notebooks for that. So basically, I'm going to allocate the array. So in this case, we want just one array X without any other shape. And we want to say, one case it's Numpy. and we are going to time function, but now with the function, it's expecting an argument. So while time, it doesn't want an argument. So I pass another lambda that it's empty, and I say this calls a function of x. So let's name it okay, so this is going to be the pure number I need to define. And the data set size is 1, and it's good to where do I have it? It's good to reset the data frame. The data frame since we don't want the other results, so it's create a new empty data frame. Okay, so this is the performance of the role. Now let's compile this one. Let's git it, and this is the next Numba. And I do the same, but now with Numba. Okay. Okay, basically, what do we see here now? We see a gain that is better than what we saw before. That is about, okay, depends a bit on the ranges. If for small data set, it's about 10 times faster, around 32 elements, this is the peak. And then when we go to large, is around 2.4 times faster. The performance, etc. So a question, why do we have this peak here at the beginning? Any idea? If I run it again, it disappeared. It's there. So the reason why that peak is there is because the first call that you do of these needs to be compiled, right? So it's not compiled. It needs to be compiled, and that was the first time we're calling it and was compiled. This is then so you need to remember to do a kind of warm up to call it first once. Then we call it and we get this speed up. Okay. So yeah, we have a great speed up compared to Numpy when we do something a bit more complicated like this. Why? Because like I was saying before, this one, it's explicitly rolling and allocating before adding, while this one, it's accessing directly the next element, right? Okay. Let's keep this an example. And let's move on to the usage of Numba for Cuda, unless there are questions. So Nicolas, you were doing like this, right? When for optimizing such a kernel. Or...
Yeah, and I also had some if there, so if and else elif, so it did a tremendous change in the performance.
Of course, yeah, of course. If you have something a bit more complicated that is more C style and you don't know how to achieve that in Python, you need to do this. Exactly, clear, very good. Okay, yeah. And the same you are going to need it if you want to run on device, of course, because like we said, Cupy provides you a one-to-one API. So the same that you are doing here, I can run it for Cupy, right? So I can do now I can say, let's stay in the purpose of the workshop, and let's run the same that I did here, but with Cupy. And then we compare after. So I can still use the same function because we saw before that empty.roll is not, does not suffer much about that. But I don't have to forget that I need to time the GPU. So just let's remind that. I time the GPU, and okay, yeah. We get a speed up compared to Numpy that is still 100 times faster, so it's good. But again, we are quite far away from the bandwidth because of the same issues you have with Numpy. So this operation is done also on device into steps, and this is especially quite computation demanding compared to this. Have in mind that this in C, or when it's compiled, it's very, very cheap because we are just saying add X to the next. It's simple. Should be simple enough also to be done in Numpy, but yeah, there is not really a way to do it unless you roll it, which means allocating, rolling explicitly, and then it's too much. Okay, rolling means doing this. It's something you don't want to do. You want, it's basically when you do roll, you are going to first roll like this, and then I'm going to do this. This is what roll does, right? So I'm first rolling and storing, and then I use the rolled one to sum element-wise. These are these two steps. It's not efficient. Should be, yeah. Okay. Next, Numba for GPUs. How does it work? Well, again, it's simple enough, but you need to have a bit an idea of how Cuda works on the also in C, basically. So it's similar. We'll do it maybe with the other example now, the roll. But the idea is that you import from Numba Cuda with a C. Now you say Cuda.JIT of a function that is an explicit function that accesses elements of your array. So just to copy, to have it here, this is how you write your for loop, right? This is how you write your for loop. This is exactly the same content, right? Just that now when you're on device, you don't want to say loop for, but you want to say to get an ID I. Okay. I want to get an IDI. This IDI Cuda offers you, Numba via Cuda offers you a more user-friendly function that is grid. That basically does for you what you were doing yesterday with Yannis, that is the product of the number of blocks times the block ID, the thread ID, etc. So this is going to give you a unique I per thread. Okay, it's doing the same stuff. And how do we run this function now? We compile it, we say JIT, we save the output, the resulting out. And then we want to call it exactly as a kernel, like this. Maybe just to make it simpler. You want to call it exactly as a kernel by saying, giving in square brackets the number of blocks and threads. So here it's m block and then threads. And then with the rounded parentheses, you give the input. Okay, any question?
Optimize then the threads. So it's up to us to.
You can put if condition on the thread on I, etc. You can do that, of course. Yeah, yeah. You can do that.
So it's not done by
you must give block and threads. It doesn't know now how to do it. You need explicit to give that that number. Okay.
And what is Cuda grid? Cuda.grid?
Yeah, it's this function that gives you the ID.
Okay, yeah.
Yeah, it's basically, sorry, I forgot to write, it's easier to get it online. So you could write explicitly the trade ID and like this, like you will do in C. So you basically have a mapping of the same API, right? You can like you were doing yesterday in the kernel. You need to get the trade ID, the block ID, the number of threads per block, and then you can compute your unique index by doing the trade ID plus the block ID and the number of threads. Anyway, this operation, this gives you the position. But since everybody does it, this is a standard. What Numba provides you is grid, and you just say grid 1. 1 is the number of dimensions, okay, and this is the same operation. If you want to give if you want to provide a multi-dimensional, if you want to use a multi-dimensional array, anyway, you want to provide X and Y. I don't know if Yannis yesterday showed you, but you can also provide per block and thread up to 3 dimensions, and you can provide X, Y, Z. So you can provide the size of the block in X and Y and Z. Then in the same way, you can use CUDA grid 2 or 3 for higher dimensionality. Okay. But basically, if you're going to use 1 dimension, use CUDA grid 1, and it's giving you the index. Other questions? Okay, then let's see. Let's see how it goes. So now just a second. Let me because now I've written it. Let me rerun these two. So now here we have the Cupy performance against the Numpy and Numba. Okay, I hope that's the correct one. And now we use Numba Cuda. So I'm doing the same thing, but by calling this function compiled by Numba. Okay, what do we see? Where did it go? Yeah. What do we see? Numba is the purple line. It's not great. It's the problem of Numba Cuda in the specific is that it has much higher overheads than the Cupy itself. So this is, I didn't find a way to reduce this overhead. So this is a very high overhead, especially for this kernel. When we compare to Cupy, that it starts from here. So all the problems are overheads. And if we go, if we now see the speed up, okay, with the speed up of this specific kernel, it's better than Numpy, of course, after some point, but it's performing worse than giving the explicit kernel of Cupy. So it has larger overheads. This is something you might hope that it gets improved with the time by the Numba developers. Maybe if I update my Numba version, this maybe already, I don't know what version I have. This maybe it's already better. Let's see. But yes, there is this issue of the overhead. On the other end, now if we scale further, anyway, I need to reload the Numba. Now nothing gets changed. I need to restart the kernel. Okay, but if we scale further, still it gets, after this overhead gets compensated by the timing, things get better. So if I go, if now I go up here, no, this one. And instead of running, sorry, just a second. I need to go up to here. Instead of running up to 25, let's go up to 26, to 26, suppose. I have Numpy, Cupy, then I have the Cupy kernel, and then I run Numba. You can see that still we get similar performance. So this is somehow a disadvantage. of using Numba. On the other end, so again, you see Numba Cuda is here. It gets faster than Cupy, the pure Cupy, up to over this number, but doesn't get as fast as a compiled Cupy kernel because of this very large overhead. On the other end, Numba offers you a much simpler way to implement more advanced kernels, like in the case that we were doing here of add next, because now this kernel, specific kernel, let's implement it in Numpy, in Numba. It's much easier. While you see, while with Cupy, going back, I hope you don't get lost. While with Cupy, we have these few versions. So we had either an element-wise kernel or a row-C style kernel, but we don't have anything in the middle. So the add to next, you cannot do it here because you cannot access components, right? You always get the local X and Y. It's impossible to be done here. On the other end, you can do it here, but then you need to manage the number of threads, the number of blocks, and do the one ID plus the next, right? So this gets more complicated and gets in C style. Numba offers you a way in the middle, and you can do the same in by using Numba and compiling the Python code. Okay, so let's try now to do it. Other questions? So I want these. No. So let's do Numba GPU. So what do I need to do? Okay, we said this is going to be cuda.git. All right. Then next, what should we need to do? Nicolas, do you want to help me?
Not sure what you're trying to do.
So I want to do a device kernel for compile with Numba, like I showed in the example below. So we want.
You need to get the grid dimension, the ID first.
Okay, so I don't have a for loop now. I need to get I equal cuda.grid of 1. Okay.
You don't need the array, I think, or I think you have to pass the array now.
Yeah, exactly. I should not do an allocation. This is now a kernel, so the output must be always given within the input, right?
Yeah.
So I need to do like this.
So these are passed as pointers, right?
Now these are pointers. You need to think about them as an array. Every array is a pointer. It should be.
Yeah, yeah. I don't know if you have to do anything else.
Okay.
You have to share the memory, or?
Well, okay. There is the issue of always illegal memory access. So now we are not doing. Also, what I wrote here actually, it's not great because I'm accessing the +1, but +1 might not exist, right? So yeah, I should loop up to -1 or have periodicity, right?
Yeah.
Okay. So how do we? When you do Cuda kernels, this gets even worse because you need to define the number of blocks and threads, and I may run over much larger dimensions, right? So like we have now in the example below, when I'm running this kernel, I'm fixing the number of threads. I will copy this. I fix the number of threads to be, let's say 256. But suppose now we run something that has dimension, has only one element, then we are running actually 256 we are still running over 256 elements. So this I gets value from 0 to 255. You don't have, even though only one is going to work. So that's indeed why one of the reasons why you don't want to run for too few elements. But still, how do we solve this issue? What do we need? Now we don't have any for loop, so we cannot control the value of I. We need an if condition. So if I is greater than the len of or x dot shape, you can access the shape of 0 minus 1, let's say, or let's say the gradual except of 0, we return. So this way we are going out of the function, right?
Okay.
And this is something you must do. And then let's put again the periodic boundaries like this. So this is a kernel that now it's an appropriate kernel.
Do GPUs generally able to handle if statements?
Yeah, of course. That you, well, you should have had yesterday an if statement like this in your kernel. It's the same. This is the part of the work of Numba in translating this as an if in a C if statement, but it's like if an if statement is C.
Yeah. Okay.
Okay. So questions? Let's try to run it. Okay, let's try to run it. What do we need to do for running it? Who's going to help me? Yeah. Do you want to help me? Open the microphone, so. Okay. Yeah. It's fine.
To run the compiled.
The compilation is going to be done the first call. It's not a problem now. We need just to call the function. Okay. So we want to run this. What do we need? We need to define the x and y, right? So
yeah, the arguments. Yeah.
Yeah, the arguments. We need to allocate them. So for this, we still use CP. We say, let's say this is random.rand of size 10. Then the y is something that is going to have the same size, right? To be null. Let's not spend time assigning values. Say CP empty like x. This is what you want to do. It is just saying something that is empty like x. Okay. And then we want to call add Numba GPU, right? Of x and y. But I think if I call it like this, it's going to complain because I didn't give block and thread. So we need to provide block and thread. What is a good value? I mean, if you, okay, you can say you have 10 blocks and 1 thread. This is going to run over all of them, and we have y. Or what else we can do? We can say 1 block and 10 thread. It's going to be to run over the same stuff. Or usually what you will do is to define the number of threads that is fixed, that you need to tune it. And then you are going to say that the arguments is the size. So this is, let's name this size, and size equal 10. So it's going to be, okay, the round up of the size divided by number of threads and number of threads. So basically in this way, we are going to run 1 block and 256 threads, which is a waste, but you are not interested to run 10 elements. Okay. So let's run it. Let's check the performance of it. And how do we call it? So we are calling it in this way now. Let's we call it in this way with X and Y explicitly. And here, this is going to be the function Numba. And basically, we know the size. We know, because the size is given here, we are locating already X. We just need to do the same for Y. We need to locate Y. And this is Numba GPU. Let's see how it goes. Is it faster than Cupy? This round it is. No, wait, Numba GPU is the red. Yeah. It is a bit faster, but it gets faster because you can see it here. If we go farther, let's go to 27. Let's go. We'll take a bit. It's going to be faster because, like we said before, and it's okay. Hopefully we get close to the performance, to the expected bandwidth. Like we said before, we have larger overheads, yes, but now what Numba is doing is compiling the kernel, compiling this function as one kernel, and not as two operations. So Cupy instead was still doing this. Writing this as a Cupy kernel would require to go to explicit row kernel like I was showing before. Okay. Okay. Questions or I show one more thing and then we are done. Do you have any question on this example? Okay, then I would like someone to help me on writing portable Numba kernel. Let's do also this bit. Namely, are we? Yeah, we are here. Namely, what do you see here? If we want to do with some kernels, let's say you're already using Numba like Nicolas does, and you want now to be able to compile this kernel for both CPU and GPU using Numba. Well, like I did here, it's a lot of copy and paste. These information are exactly the same, correct? This is the same in C. So if you want to write it in a portable manner, what will you do?
Make the inner part of the loop a function.
So yeah, making the content of the loop a function. Perfect. Let's do it. So we remove completely the for loop. Now it's something that takes us out as an argument, and we untab it, and this is the content of the loop. Next, what do we need to do? So this, let's name it inner. Then what do we want to do? We want to write one function for CPU that looks like this. So the CPU, we don't want to change the behavior. So we want a CPU version of it that still takes only 3 arguments, and the third is optional. So let's say out equal none. What does this one have to do?
We need the grid.
No, the grid is for the GPU. This is CPU. we need to put the for loop. So we need to allocate out. Basically, we need to take the content of this, allocate the out. Then here we want to call the other part, the other bit we've written. I need to provide I as argument. Perfect. So I'm going to provide out up to here, and I provide also I. Okay. So we were missing one argument. And then I say return out. So this does exactly the same of the other, right? If we want to have this optional, if we want to give the option to provide us the output, what we do? We just check if out is known, we allocate. Otherwise, we use it. So these avoid the allocation because one is providing out. Okay, and then if we want to use Numba for it, we need to JIT it, right? Okay, let's do the same for GPU now. What do we do? Yeah, we don't have the for, we have the I, we use I. Then we want to say, we want to have the if condition that if I is greater than an array, the size, we go out. And then we just simply call the input, this one, okay? Okay, so this is a way to define a portable kernel, let's say, right? With the minimal, so you have the kernel, this is what you will name the device kernel. And then here you can keep elaborating. So this can be anything that is a function of those parameters. And then you have two versions, one from CPU, one for Cuda, that are going to run the kernel. And they are both compiled. Okay. Yeah, you should check if you don't want to compile these. Okay, yeah, this is another good question. So this is not still yet generic. It's not, one, it's not a replacement of the other, because one, you just call it. The other, you need to provide the block and the thread. So you need another layer that takes care of that. If you want to define a rot shift that is agnostic on CPU or GPU. The point of this up to here was to do not repeat code. And in case you do a mistake on one kernel, this is what you have to do. This is what you want to do. You don't want to write code twice because maybe you did a mistake, then you forget to change. You change only one piece. You forget to change the other, etc., etc. So you don't want to do. You don't want to write code multiple times, right?
If we use GPU, for example, to check if.
Yeah, of course. The bit you want to avoid because you're on GPU to compile this guy. But I think Numba Cuda itself, you cannot import it unless you are on device already. So I had here this example. If I say import Numba, this I can import it because it works for CPU and GPU. But if I say from Numba import Cuda, I guess this one wants to import, no, it works. It still works, but at the moment you try to run Cupy, and itself will not work. So yeah, it's a cost that you can avoid if you put an if condition, sure. Okay, any question? Otherwise we close.
A more general question. What if you want these functions to be within a class? Is there any difference? Because there you also have this self.
Okay, well, the self is not a okay. The self is not a problem. So within a class, okay, this is a good question. But the method of within a class, when you define a function, even if it gets self, this one, you can still JIT it. As far as the self, so the content of the class is, it does not, I mean, it's pure Python. It does not depend on any unknown compiled library, let's say. Why you can still JIT it? Because this guy here, the self itself, it's nothing special. So the okay, this we go into the details of Python. So when we let me remove the JIT for now, just for this example. So foo.fnc, okay, it's a function. It's a function that you can call with anything. I can provide one. Doesn't have to be self an instance of foo. Okay, I can provide it any input, and the self is just the input. So the self is just a standard name that you give for the first argument of a class, because it's going to be the instance. But it can be anything. You can name it A, and Python doesn't care about that. Okay. So you should see the functions still as functions. The difference of a method that is a class method, so where you put self, is that if you take the function, that you access the method not from the class, so foo is the class, right?
Yeah.
But of an instance of the class, okay, when I access this is from the instance of the class, then definitely it's not a function anymore, but it's a bound method of foo, of foo function, that it's going to give the instance as a first argument to the function. Do you see it? So when I do this, it's this bound method. So you can actually, if you say a dot, you can access, if I remember correctly, it's named self. This is the instance of the class. So this is a bound method. So A is the instance of the class. And I think FNC should be the func is the function that you're going to call. So it's just another class that has self as function as arguments and it's overwriting how you're going to call it. So it's overwriting this call. But that's just how Python works, the bound method. But this is not C, it's not self must be an instance, it's a function. So JIT knows what to do. As far as then the self you get, you give is something that JIT knows how to handle.
If your self contains Python objects, for example,
you can have,
dictionaries, for example.
It's still fine, it knows how to compile JIT.
But if you give it pandas,
if I give it pandas
data frame,
if you give pandas, it's a problem.
Yeah, I mean, will it be a problem if the self in general, the instance that I create has a pandas attribute, but within the function I don't use it?
Exactly. As far as you don't access it within the function, it's fine.
Oh, okay.
I think so. You should try and let me know.
Okay.
Because it's not going to translate self completely. It's just going to look at what you are going to access.
Yes.
So important. It's done at runtime, so it's compiled at runtime. So you provide a self, it checks what self is, and then compiles a kernel. So it's
okay.
Yeah. Other questions? Okay, then we can close, and we later, day after, you are going to have a session on Julia. So this was the part on Python.
Okay, so we meet back at 2 o'clock in about 55 minutes time.
Thank you.
Bye.